There is an object in the universe that should not exist, not because it breaks a single law of physics, but because it pushes every law to its absolute limit, until the line between reality and impossibility begins to blur. It is not as large as a galaxy, not as dramatic as a black hole, and yet, in many ways, it is far more disturbing. Because unlike a black hole, where everything disappears beyond a horizon we cannot see, this object remains visible, exposed, measurable, real, and inside it. Matter itself is no longer what we understand it to be. Imagine taking something as massive as the sun, over 300,000 times the mass of Earth, and compressing it into a sphere no wider than a city. Not a country, not a continent. A city. A place you could drive across in less than an hour. And yet, within that space, exists more mass than we can truly comprehend. This is a neutron star. At first glance, the idea feels abstract. Numbers without meaning, scales too large to picture. But the reality is far more unsettling when you slow down and truly consider what it implies. If you were to stand on the surface of a neutron star, even for a fraction of a second, the consequences would not simply be fatal. They would be absolute. Gravity there is not just stronger than Earth's. It is billions of times stronger. Every step you take would feel like the weight of an entire mountain pressing down on your body. Your bones would not break. They would collapse. Your atoms would not separate. They would compress. Even light itself struggles to escape. Time slows down. Space bends. And yet, this is only the surface. Because the real mystery is not what we can see. It is what lies beneath. Inside a neutron star, the familiar structure of matter, atoms, nuclei, particles, begins to dissolve into something else. Something we do not fully understand. Something that may not even have a name. Physics, as we know it, starts to lose its clarity. Equations still exist, but their meaning becomes uncertain. Predictions become possibilities. Possibilities become questions, and questions remain unanswered. What happens inside a neutron star? It sounds like a simple question, but it leads us into one of the deepest mysteries in modern science. A place where gravity, quantum mechanics, and the very nature of matter collide in ways we are only beginning to explore. And to understand why this question is so difficult, we need to begin somewhere familiar. Not with something extreme, but with something ordinary. A star. Every star in the night sky, even the faintest one, is powered by a simple process. At its core, hydrogen atoms collide and fuse, forming helium. In that process, a small amount of mass is converted into energy. That energy pushes outward. Gravity pulls inward. And for millions, or even billions of years, those two forces remain in balance. A quiet, stable equilibrium. But this balance is not permanent. Stars are not eternal. And when the fuel begins to run out, the equilibrium starts to break. Slowly at first, then all at once. In massive stars, those far larger than our sun, the ending is not gentle. It is violent beyond imagination. As fusion slows, the outward pressure weakens. Gravity, on which has been waiting patiently the entire time, begins to take over. The core starts to collapse, faster and faster. Atoms that once existed comfortably, with space between their particles, are suddenly forced together under unimaginable pressure. Electrons are pushed into protons, charges disappear, structures collapse, and something new begins to form. But we're getting ahead of ourselves. Because before we can understand what happens inside a neutron star, we need to understand just how extreme this object really is, not in abstract terms, but in ways that can be felt, imagined, almost experienced. Let's start with something simple. A single teaspoon. On Earth, a teaspoon of sugar weighs only a few grams, light enough to hold without noticing. But a teaspoon of neutron star material? It would weigh around 1 billion tons. Well, that's not a metaphor. That's not exaggeration. That is the actual estimate based on what we know. Now pause for a moment. A single teaspoon. Something small enough to sit on your fingertip, weighing more than Mount Everest. And yet, even that comparison doesn't fully capture it, because the weight isn't just heavy, it's dense, unimaginably dense. On Earth, most of what we perceive as solid is actually empty space. Atoms are mostly void, with tiny nuclei surrounded by distant electrons. If you could remove that empty space, everything around you would shrink dramatically. A human body would collapse into something smaller than a grain of sand. A mountain would become microscopic. Inside a neutron star, that empty space is gone. Completely gone. Atoms no longer exist in the way we understand them. Electrons have been crushed into protons. Protons and neutrons are packed together. Matter becomes something closer to a continuous structure than a collection of particles. A kind of cosmic compression. And this raises a question that is as unsettling as it is fascinating. If matter can be compressed this far, what happens next? Does it stop? Does it reach a limit? Or does it continue collapsing into something even stranger? This is where neutron stars become more than just extreme objects. They become boundaries, natural laboratories where the universe tests the limits of its own rules. Scientists have spent decades studying neutron stars, observing their radiation, measuring their mass, tracking their behavior. And yet, even with all of that data, the interior remains largely unknown. Not because we lack intelligence, but because the conditions inside a neutron star cannot be recreated on Earth. Not even close. The most powerful particle accelerators, machines designed to probe the smallest building blocks of matter, can only simulate tiny fragments of these conditions for fractions of a second. A neutron star sustains them continuously, across an entire celestial object. So instead of direct observation, we rely on theory, on models, on equations that attempt to describe what happens when matter is pushed beyond every familiar boundary. Some of these theories suggest that inside a neutron star, particles dissolve into even smaller components, quarks, forming a kind of exotic matter unlike anything we have ever observed directly. Others suggest new states of matter entirely, structures that behave in ways that challenge our understanding of physics itself. And yet, despite all of this complexity, the question remains simple. What happens inside? It is a question that pulls us deeper, from the surface into the crust, from the crust into the core, from the core into the unknown. But before we can go there, we need to witness the moment when all of this begins. The moment when a normal star, something stable, familiar, predictable, collapses into something far more extreme. Because neutron stars are not born quietly. They are created in one of the most powerful events in the universe. An explosion so bright, it can outshine entire galaxies. An event that marks both an ending and a beginning. And to understand what happens inside a neutron star, we must first understand how it comes into existence. A neutron star does not begin as something strange or exotic. It begins as a star, massive, bright, and stable, existing for millions of years in a delicate balance that seems almost unbreakable. For most of its life, nothing about it suggests the extreme object it will eventually become. It shines like countless other stars, powered by the same fundamental process that governs much of the visible universe. At its core, energy is produced through nuclear fusion. Hydrogen atoms collide under immense pressure and temperature, merging to form helium. In that process, a small amount of mass is converted into energy, released as light and heat. This energy pushes outward, resisting the inward pull of gravity. The star exists in equilibrium, held together by a constant tension between collapse and expansion. For a long time, this balance is stable. The star appears unchanging from the outside. But deep within its core, a quiet transformation is taking place. Hydrogen is slowly consumed. The fuel that sustains the star is being used up, atom by atom, reaction by reaction. What appears constant is, in reality, a gradual process of depletion. As hydrogen becomes scarce in the core, fusion begins to slow. The outward pressure that once held gravity in check weakens, even if only slightly at first. Gravity responds immediately. It does not need to build strength or accelerate its influence. It is always present, always pulling inward, waiting for the moment when resistance fades. The core begins to contract. This contraction is not sudden. It is a slow tightening, a gradual increase in density and temperature. As the core compresses, conditions become more extreme. Temperatures rise high enough to ignite new forms of fusion. Helium begins to fuse into heavier elements like carbon and oxygen. For a time, the balance is restored. The star stabilizes again, powered now by a different fuel. But this is only temporary. Each stage of fusion produces heavier elements, and each stage is shorter than the last. Hydrogen burning may last millions or billions of years. Helium burning lasts far less. As the core continues to evolve, new fusion processes ignite in sequence, forming neon, magnesium, silicon, and eventually iron. Iron marks a turning point that cannot be reversed. Unlike lighter elements, iron does not release energy when fused. Instead, it consumes energy. This means that once the core becomes dominated by iron, fusion can no longer support the star. The outward pressure that once balanced gravity disappears completely at the core. What remains is a star with enormous mass and no internal force strong enough to resist its own gravity. At that moment, collapse becomes inevitable. The core begins to fall inward under its own weight. What was once a gradual process becomes sudden and unstoppable. The scale of this collapse is difficult to comprehend. The core, which may be thousands of kilometers across, begins shrinking rapidly. Gravity accelerates the process, pulling matter inward faster and faster. As the core contracts, its density increases dramatically. Atoms are pushed closer together, and the empty space within them begins to vanish. Electrons, which once occupied vast regions around atomic nuclei, are forced into tighter and tighter confines. The distinction between separate atoms begins to blur. Temperature rises to extraordinary levels. The collapsing core becomes one of the hottest places in the universe, not because of fusion, but because of compression. The energy released by the collapse itself drives temperatures upward. Then something even more extreme begins to happen. The pressure becomes so great that electrons can no longer remain separate from protons. Under these conditions, the fundamental structure of atoms breaks down completely. Electrons are forced into protons, combining to form neutrons. This process, known as inverse beta decay, changes the very nature of matter. Charges disappear. The balance between positive and negative is erased. What remains are neutral particles, neutrons, packed together with incredible density. But this transformation does not happen slowly. It occurs in a fraction of a second, as the collapsing core reaches conditions beyond anything found in normal stars. Matter is no longer made of atoms. It is becoming something else entirely. At the same time, another process unfolds around the collapsing core. The outer layers of the star, which have been held in place by the pressure from within, suddenly lose their support. Gravity pulls them inward as well, causing them to crash toward the center at enormous surround. But they do not reach it. As the core collapses and stiffens under the pressure of neutron formation, it reaches a point where further compression becomes extremely difficult. The neutrons resist being packed any closer together due to quantum mechanical effects. This resistance creates a sudden halt in the collapse, but the inward falling outer layers slam into this dense core. The result is one of the most powerful explosions in the universe, a supernova. The energy released in this event is staggering. In a brief moment, the star releases more energy than it has emitted over its entire lifetime. Light floods outward, carrying the signature of the explosion across vast distances of space. For a short time, the dying star can outshine entire galaxies. Shock waves ripple through space, pushing matter outward at incredible speeds. Elements formed in the star's core are scattered into the surrounding universe, seeding future stars and planets. What was once a single star becomes a cloud of expanding debris, illuminated by the energy of its own destruction. At the center of this explosion, something remains. The core, now composed largely of neutrons, has survived the collapse. It is no longer a star in the traditional sense. It no longer produces energy through fusion. It is something far denser, far smaller, and far more extreme. A neutron star has been born. But even this description does not fully capture the intensity of the transformation. The entire process, from stable star to collapsing core to supernova explosion, unfolds in a matter of seconds. A structure that existed for millions of years is destroyed and remade almost instantly. What remains is an object that defies ordinary understanding. Its size is drastically reduced, yet its mass remains enormous. Gravity becomes so strong that it alters the flow of time and the path of light. The matter within it is no longer composed of recognizable structures. It exists in a state that challenges the limits of physics. And yet, this is only the beginning. Because while the explosion marks the end of the star's life, it also marks the beginning of something far more mysterious. The neutron star that forms in the aftermath is not static. It is not simple. It contains layers, structures, and behaviors that are still being studied and debated. To understand what happens inside it, we must move closer. We must examine not just its origin, but its physical form, its surface, its structure, the way it exists in space. Because what appears from a distance as a small, dense object is, in reality, a world of extremes unlike anything else in the universe. The collapse of a massive star does not end quietly. It does not fade or dim or slowly disappear into darkness. Instead, as it produces one of the most violent and luminous events in the universe. An explosion so powerful that, for a brief moment, it can outshine entire galaxies. This is the supernova. It begins at the exact instant when the collapsing core can no longer compress any further. As gravity forces matter inward, densities rise to an extreme point where the newly formed neutron-rich core becomes almost incompressible. The particles inside are packed so tightly that further collapse is resisted not by ordinary forces, but by the fundamental rules of quantum mechanics. The inward motion stops, but the outer layers of the star do not. They are still falling. For a fraction of a second, The entire structure of the star is out of sync. The core has halted, but the rest of the star is still collapsing inward at tremendous rate. When these outer layers crash into the rigid core, the energy of that motion has nowhere to go. It reverses direction. What follows is not a simple rebound, but a catastrophic release of energy. A shock wave forms at the boundary between the core and the infalling material. This shock wave begins to move outward, pushing against the collapsing layers above it. At first, it struggles. The density of the surrounding material is enormous, and the shock wave begins to lose energy as it moves outward. For a brief moment, it appears as though the explosion might fail, that the star might collapse entirely inward instead of exploding outward. But something else is happening at the same time. As the core compresses and neutrons form, an enormous number of neutrinos are produced. These particles are incredibly small, nearly massless, and interact only weakly with matter. Under normal conditions, they pass through entire planets without being stopped. But inside a collapsing star, even neutrinos begin to matter. The core releases an immense burst of neutrinos, carrying away a significant portion of the gravitational energy released during collapse. Trillions upon trillions of these particles stream outward in every direction. Most escape into space, but some interact with the surrounding material, and that interaction is enough. The energy deposited by neutrinos into the outer layers of the star re-energizes the weakening shock wave. It gains strength again, pushing outward with renewed force. What was once a failing collapse becomes a successful explosion. The star tears itself apart. Layers of gas, plasma, and heavy elements are hurled into space at speeds reaching thousands of kilometers per second. The explosion expands rapidly, forming a glowing shell that continues to grow over time. This expanding cloud, known as a supernova remnant, carries the material of the star outward into the surrounding cosmos. Inside that expanding debris are the building blocks of future worlds. Elements heavier than iron, gold, uranium, and many others are formed during the explosion itself. The extreme conditions of temperature and pressure allow nuclear reactions that cannot occur under normal stellar conditions. These elements are scattered across space, eventually becoming part of new stars, planets, and perhaps even life. In this way, the destruction of one star becomes the origin of countless others. But while the outer layers are thrown outward, the core remains behind. And what remains is no longer a star in the traditional sense. It is something far smaller, far denser, and far more extreme. The newly formed neutron star is born in the aftermath of chaos. It is surrounded by expanding debris, intense radiation, and rapidly changing magnetic fields. For a time, it is incredibly hot, millions of degrees, glowing with the residual heat of its own formation. But despite the violence of its birth, the neutron star itself is remarkably stable. Its structure is defined not by fusion, but by balance. Gravity continues to pull inward, just as it always has. But now, instead of being resisted by thermal pressure from fusion, it is opposed by neutron degeneracy pressure. A quantum mechanical effect that arises from the behavior of particles at extremely high densities. Neutrons, like all fermions, cannot occupy the same quantum state. This creates a resistance to compression that does not depend on temperature. It is a fundamental property of matter itself, emerging only under extreme conditions. This pressure halts the collapse. For stars within a certain mass range, this balance is enough to prevent further collapse. The neutron star remains stable, neither expanding nor collapsing into a black hole. But this stability exists at the very edge of possibility. If the mass of the core had been slightly greater, even neutron degeneracy pressure would not have been enough. Gravity would have continued its work, compressing matter further until no known force could stop it. The result would not have been a neutron star, but a black hole. And this narrow boundary between outcomes makes neutron stars particularly significant. They exist at a threshold, just below the point where gravity completely overwhelms all resistance. They are, in a sense, the last stage of matter before total collapse. The explosion that created the neutron star continues to evolve long after the initial event. The expanding shell of gas interacts with the surrounding interstellar medium, creating complex structures of shock waves and turbulence. Over time, these remnants can span light years, glowing in different wavelengths as they cool and disperse. At the center, the neutron star begins its own evolution. It rotates, and it does so incredibly fast. Because of the conservation of angular momentum, the collapse of the core causes its rotation to speed up dramatically, because what may have been a slowly rotating star becomes a rapidly spinning neutron star, sometimes rotating dozens or even hundreds of times per second. This rapid rotation, combined with an intense magnetic field, produces beams of radiation that sweep through space like cosmic lighthouses. When these beams are aligned with Earth, they are detected as regular pulses, leading to the name pulsar. These pulses are among the most precise signals observed in astronomy, allowing scientists to study neutron stars with remarkable accuracy. But even with these observations, much of the neutron star remains hidden. The surface can be studied through its radiation. The magnetic field can be measured through its effects. The rotation can be tracked through timing. But the interior, the place where matter has been compressed beyond recognition, remains inaccessible. We cannot see inside. We cannot send probes. We cannot recreate the conditions. All we can do is infer. And yet, the clues are there. The behavior of the neutron star, its mass, its radius, its temperature, provides indirect evidence about what lies within. By studying these properties, scientists attempt to build models of its internal structure. These models suggest that the neutron star is not uniform. It is layered, with each layer representing a different state of matter under increasing pressure. At the outermost level is the crust, a solid region composed of nuclei and electrons arranged in a dense lattice. Beneath that, the structure begins to change. The pressure increases to the point where atoms can no longer exist in their normal form. Neutrons begin to leak out of nuclei, forming a fluid-like environment. Deeper still, the matter becomes even more extreme. Neutrons dominate, forming a dense, superfluid interior, where the behavior of matter is governed by quantum effects on a macroscopic scale. And at the very center, the conditions may become so extreme that even neutrons break down into their constituent parts, quarks, creating a state of matter that has never been directly observed. But these are only models. They are based on theory, supported by observation, but not confirmed by direct evidence. And that uncertainty is what makes neutron stars so compelling. They are not just objects in space, they are questions. The supernova marks the transition from a familiar star to an object that challenges our understanding of physics. It is the moment when matter is pushed beyond its limits, when gravity reshapes structure at the smallest scales, and when the universe reveals one of its most extreme possibilities. But the explosion itself is only the beginning. Because once the neutron star is formed, the real mystery begins. Not in the violence of its birth, but in the quiet, continuous existence that follows. A dense, compact object, spinning in space, holding within it conditions that cannot be reproduced, cannot be directly observed, and cannot be fully understood. To explore what happens inside it, we must move closer still, beyond the explosion, beyond the formation, toward the surface itself. To understand what truly happens inside a neutron star, there is a moment we must slow down and examine carefully. It is not the explosion, not the brightness of the supernova, and not even the final compact object that remains. It is the exact instant during collapse, when matter itself begins to fail, when the familiar structure of the universe quietly disappears. Up until this point, everything behaves according to rules we recognize. Atoms exist. Electrons orbit nuclei. Space, even when compressed, still allows structure to remain intact. But as the core of a dying star collapses under its own gravity, there comes a stage where pressure and density reach levels so extreme that these rules no longer apply. The collapse accelerates rapidly. Gravity pulls inward without resistance, and the core shrinks in size while its mass remains nearly the same. This causes density to rise dramatically. The atoms, which are mostly empty space, are forced closer together. The distance between nuclei decreases, and electrons are pushed into tighter and tighter regions. At first, the compression affects the outer structure of atoms. Electron clouds are squeezed, their energy levels shifting as they are confined into smaller spaces. But there is a limit to how much they can be compressed while still remaining separate from the nucleus. Eventually, that limit is reached. When it is, something extraordinary happens. Electrons are forced directly into protons. Under normal conditions, electrons and protons exist as separate particles, held together within atoms by electromagnetic forces. But under the immense pressure inside a collapsing stellar core, these distinctions begin to vanish. The energy becomes so high and the space so limited that electrons can no longer remain independent. They combine with protons. The result is the formation of neutrons. This process is known as inverse beta decay, and it represents one of the most dramatic transformations of matter in the universe. It is not simply a rearrangement of particles. It is a fundamental change in their identity. Positive charge and negative charge cancel out. What remains are neutral particles, neutrons, packed tightly together. In this moment, the concept of an atom ceases to exist. There are no longer electrons orbiting nuclei. There are no longer distinct elements with chemical properties. The periodic table, which describes the behavior of matter under ordinary conditions, becomes irrelevant. Matter has entered a new state. This transformation happens incredibly quickly, unfolding in a fraction of a second as the core collapses. The scale is enormous, involving a mass greater than that of the Sun. Yet the change occurs with astonishing surety. The entire core becomes a dense assembly of neutrons, compressed into a volume far smaller than anything that previously existed. But even this description does not fully capture what is happening, because the formation of neutrons is not the end of the process. It is only the beginning of a deeper transition. As more electrons are forced into protons, the number of neutrons increases rapidly. The core becomes dominated by neutron matter, with only small amounts of other particles remaining. The pressure continues to rise, and the density approaches values that challenge our understanding of physics. At these densities, the behavior of matter is governed not by classical forces, but by quantum mechanics. Particles are no longer independent entities moving through space. They exist as part of a highly compressed system where their positions and energies are constrained by fundamental principles. The distinction between individual particles becomes less clear. Matter behaves more like a continuous medium than a collection of discrete objects. This is a key moment in the formation of a neutron star. It marks the point where ordinary matter, atoms, elements, structures, has been completely replaced by something else. Something denser, something more uniform, something far more extreme. And yet, even here, the collapse does not simply continue without limit. As neutrons are packed together, they begin to resist further compression. This resistance is not due to temperature or pressure in the conventional sense. It arises from the quantum mechanical properties of neutrons themselves. Like electrons, neutrons are fermions. They obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state at the same time. As the density increases, neutrons are forced into higher and higher energy states, creating a pressure that opposes further compression. This is neutron degeneracy pressure. It is the force that halts the collapse of the core. Without it, the star would continue collapsing indefinitely, eventually forming a black hole. But in stars of certain masses, neutron degeneracy pressure is strong enough to counteract gravity, at least temporarily. The core stabilizes, and in that stabilization, a neutron star is born. But the idea of stability here is misleading. This is not a calm or gentle equilibrium. It is a balance maintained under conditions so extreme that even small changes could disrupt it. The neutron star exists at the edge of what is physically possible, held together by forces that only emerge under the most intensive roof. Inside it, matter is no longer familiar. It is compressed to the point where structure has been erased. It is governed by rules that are difficult to test and even more difficult to observe directly. It exists in a state that challenges our understanding of what matter can be. And yet, this is only the outer layer of the mystery. Because while the transformation from atoms to neutrons is dramatic, it does not answer the deeper question: what happens beyond this point? As pressure continues to increase toward the center of the neutron star, even neutrons themselves may begin to change. The forces holding them together may be overcome, leading to new states of matter that are even more exotic. But before we can explore those possibilities, we must first understand the structure that forms after this transformation. The neutron star is not uniform. It is layered, with each layer representing a different stage of compression and a different behavior of matter. The outer regions, while extreme, still retain some recognizable properties. The deeper regions become increasingly unfamiliar. To understand what happens inside, we must move step by step, beginning at the surface and working inward. Because the surface of a neutron star is not like any surface we know. It is not fluid like a gas giant, not molten like a young planet, but something far more rigid, far more compressed, and far more alien. After the violence of the supernova, after the collapse and the transformation of matter itself, what remains is something unexpectedly quiet. At the center of the expanding debris, where chaos once dominated, there now exists a compact, stable object. It no longer burns with fusion. It no longer expands or contracts in dramatic ways. Instead, it simply exists, dense, small, and incredibly powerful. This is the moment a neutron star is truly born. What makes this object so extraordinary is not just how it forms, but how it manages to remain stable at all. The collapse that created it was immense, driven by gravity so strong that it crushed atoms out of existence. And yet, the process stops just short of total destruction. The neutron star does not become a black hole. Instead, it reaches a delicate balance. Gravity continues to pull inward with enormous force, attempting to compress the matter even further. But opposing this is neutron degeneracy pressure, a quantum mechanical effect that arises from the nature of neutrons themselves. These particles resist being forced into identical states, creating a kind of pressure that does not depend on heat or motion, but on the fundamental rules governing matter. This balance defines the neutron star. It is not held up by energy, like a normal star. It is held up by the limits of physics. The size of this object reflects that balance. Despite containing more mass than the Sun, a neutron star is typically only about 10 to 20 kilometers in radius. And this means that an amount of matter that once filled a vast region of space has been compressed into something no larger than a city. To put this into perspective, if Earth were compressed to the same density, it would shrink to a sphere only a few hundred meters across. Everything, oceans, mountains, atmosphere, would collapse into a volume smaller than a stadium. But unlike Earth, a neutron star retains its mass. And with that mass comes gravity. The gravitational field at the surface of a neutron star is so strong that it alters the very fabric of space and time. Light leaving the surface loses energy, shifting toward lower frequencies. Time itself passes more slowly compared to distant observers. The star exists in a region where the effects of relativity are not theoretical, but immediate and measurable. Yet despite these extreme conditions, the neutron star does not collapse further. This raises an important question. Why does it stop here? Why does matter resist gravity at this point, but not beyond? The answer lies in the interplay between quantum mechanics and gravity. Neutron degeneracy pressure increases as density increases. As neutrons are forced closer together, they are pushed into higher energy states, creating resistance. For neutron stars below a certain mass limit, this resistance is enough to counteract gravity. But there is a threshold. If the mass of the collapsing core exceeds this limit, known as the Tolman-Oppenheimer-Volkoff limit, then neutron degeneracy pressure is no longer sufficient. Gravity overwhelms all known forces, and the object continues collapsing into a black hole. This makes neutron stars unique. They exist in a narrow range of possibilities, balanced between stability and total collapse. They are the last stage where matter can still exist as a physical substance, before being crushed into something even more extreme. The newly formed neutron star is also incredibly hot. The collapse and subsequent reactions release vast amounts of energy, leaving the star with temperatures reaching millions of degrees. Over time, it will cool, radiating energy into space, but this process can take thousands or even millions of years. In its early stages, the neutron star is highly dynamic. It may rotate rapidly, sometimes hundreds of times per second. This rapid rotation is a direct result of the collapse. As the core shrinks, its rotational speed increases, much like a spinning object that pulls its mass inward. This rotation, combined with an intense magnetic field, gives rise to some of the most fascinating phenomena in astrophysics. The magnetic field of a neutron star can be trillions of times stronger than Earth's. In certain cases, known as magnetars, the field becomes so powerful that it can distort atoms and affect the vacuum of space itself. Radiation is emitted along the magnetic poles, forming beams that sweep through space as the star rotates. When these beams intersect with Earth, they are detected as pulses of radiation, leading to the classification of these objects as pulsars. These pulses are incredibly regular, allowing scientists to measure time with extraordinary precision. Some pulsars are so consistent that they rival atomic clocks in accuracy. Through these signals, we gain insight into the behavior of neutron stars, even though we cannot directly observe their interiors. Despite this wealth of information, much remains hidden. The neutron star appears as a simple object from a distance, a small, dense sphere emitting radiation and rotating in space. But this simplicity is deceptive. Beneath the surface lies a structure of immense complexity, shaped by pressures and densities that vary dramatically with depth. The outermost layer, known as the crust, retains some resemblance to ordinary matter. It is composed of nuclei and electrons arranged in a lattice, though under far greater duct than anything found on Earth. This crust is incredibly strong, far stronger than any material we can produce. But as we move inward, the structure begins to change. Pressure increases, density rises, and the familiar forms of matter begin to dissolve. The deeper layers of the neutron star are not simply denser versions of the surface. They are fundamentally different. Each layer represents a transition to a new state of matter, governed by conditions that push physics to its limits. This layered structure is key to understanding what happens inside a neutron star. It is not a uniform sphere of neutrons. It is a complex system with distinct regions that behave in different ways. The transitions between these regions are not always smooth. In some cases, they involve abrupt changes in density or composition. These boundaries are where some of the most interesting physics occurs. And yet, we cannot see them. All of our knowledge comes from indirect observation and theoretical models. We infer the internal structure based on how neutron stars behave, how they rotate, how they emit radiation, how they respond to external forces. This makes the study of neutron stars both fascinating and frustrating. We are observing something real, something measurable, but much of its nature remains hidden behind layers we cannot penetrate. To move closer to understanding, we must examine each layer individually. We must start at the surface and work our way inward, exploring how matter behaves under increasing pressure and density. Because while the birth of a neutron star marks the beginning of its existence, it also marks the beginning of a deeper mystery. What lies beneath the surface is not simply compressed matter. It is a sequence of transformations, each one more extreme than the last. And each one brings us closer to answering the question that started this journey. What happens inside a neutron star? Once a neutron star is formed and the chaos of its birth begins to settle, what remains is an object that appears, at least from a distance, almost simple. A small, dense sphere drifting through space, rotating steadily, emitting radiation in precise intervals. But this simplicity is deceptive. Because the moment we move closer, closer than observation usually allows, the reality becomes far more extreme. The surface of a neutron star is not like the surface of anything we know. It is not liquid like an ocean, nor gaseous like the atmosphere of a star. It is not even molten, despite the immense heat left over from its formation. Instead, it is something far more rigid, far more compressed, and far more powerful than any material that exists naturally on Earth. It is, quite literally, the strongest surface in the known universe. To understand why, we have to consider the conditions under which it exists. Gravity at the surface of a neutron star is so intense that it pulls everything inward with extraordinary force. Any structure that remains stable under such conditions must be able to withstand pressures far beyond anything encountered elsewhere. And yet, the surface does remain stable. It forms a solid crust composed primarily of tightly packed nuclei and a sea of highly compressed electrons. These nuclei are arranged in a lattice structure, somewhat similar in concept to the crystalline structures found in metals on Earth, but far more dense and far more resistant to deformation. The strength of this crust is almost impossible to visualize. On Earth, the strongest materials we know, steel, diamond, advanced composites, can withstand immense stress. But under the gravity of a neutron star, they would not simply break. They would cease to exist as structured materials. Their atomic bonds would collapse instantly under the duct. The crust of a neutron star, however, holds together. Estimates suggest that it is billions of times stronger than steel. Not just harder, but more resistant to deformation, fracture, and compression. It is a material formed under conditions that cannot be replicated, structured by forces that operate at the very limits of physics. But even this description only captures part of the reality, because the surface is not smooth. Despite the immense gravity, which tends to flatten structures, there are irregularities. There are variations, but these variations are extremely small. Mountains on a neutron star, if they can even be called that, are measured in centimeters rather than kilometers. A structure just a few centimeters tall would already represent a significant deviation from equilibrium. Gravity ensures that nothing can rise much higher. Everything is pulled down, compressed, and flattened into near perfection. Now imagine, for a moment, approaching this surface, not as an observer from afar, but as something moving closer, entering the gravitational field, descending toward this extreme environment. At first, the effects are subtle. Gravity increases gradually. Your weight becomes noticeable, then heavy, then overwhelming. Movements slow. Every step requires more effort than the last. The pull downward becomes inescapable. As you continue closer, the difference becomes dramatic. Your body, which evolved under Earth's gravity, is not designed for this. Bones strain under the increasing load. Muscles can no longer support movement. Internal structures begin to compress. But this is only the beginning, because gravity does not act equally across your entire body. The difference in gravitational pull between your head and your feet becomes significant. This creates a stretching effect, pulling you apart at the same time as it compresses you. This process, often referred to as spaghettification, begins long before you ever reach the surface. By the time you are close enough to touch it, the concept of a human body no longer applies. Matter is being pulled, stretched, and compressed simultaneously. And yet, the surface itself remains unchanged, unyielding. If something were to actually make contact with the surface, the interaction would be immediate and absolute. There is no soft landing, no gradual absorption. The object would collide with a solid structure under immense gravitational acceleration. The energy released in that collision would be enormous, far beyond anything experienced in ordinary impacts. And the surface would barely respond. Its strength is such that it does not easily deform. Instead, the incoming matter is forced to adapt, to compress, to conform to the conditions imposed by the neutron star. Atoms are crushed. Structures collapse. Matter becomes part of the star. But the surface is not just defined by its physical strength. It is also shaped by the extreme environment surrounding it. The temperature, while cooling over time, remains incredibly high compared to most objects in space. Radiation is constantly emitted, carrying away energy. Magnetic fields, often billions or trillions of times stronger than Earth's, interact with particles at the surface, influencing their behavior in ways that are difficult to predict. In some neutron stars, particularly magnetars, the magnetic field is so intense that it begins to affect the structure of atoms themselves. Electron orbitals are distorted, stretched along magnetic field lines. The very concept of atomic shape changes under these conditions. This means that even at the surface, matter is not entirely normal. It exists under influences that alter its fundamental properties. And yet, despite all of this, The surface is only the outermost layer. It is, in many ways, the most familiar part of the neutron star. Because beneath it, things begin to change in ways that are far less intuitive. As we move inward, pressure increases rapidly. The structure of the crust begins to shift. The neat lattice of nuclei and electrons becomes unstable under the growing density. Neutrons begin to escape from nuclei, forming a new kind of environment where matter behaves less like a solid and more like something in between. The transition is gradual at first, but it leads to one of the strangest states of matter ever theorized. A state where nuclei stretch, deform, and merge into complex shapes that resemble structures more familiar from biology than from physics. This is the beginning of what scientists call nuclear pasta. But before we reach that point, it is important to understand what the surface represents. It is the last place where matter still retains any recognizable structure. The last boundary between the familiar and the unknown. Above it, we can still describe things in terms of atoms, materials, and forces we understand. Below it, those descriptions begin to fail. The surface of a neutron star is not just a boundary in space. It is a boundary in understanding. It marks the point where our everyday experience of matter ends, and where the universe begins to reveal something far more extreme. Something that challenges not only our intuition, but the very framework of physics itself. The surface of a neutron star already pushes matter to its limits, but the environment surrounding it introduces something even more unsettling. It is not just matter that behaves differently near a neutron star. Time itself begins to change. Space bends. Light struggles. The rules that feel constant in everyday life begin to shift in subtle but profound ways. To understand this, we have to move beyond the idea of gravity as simply a force pulling objects downward. In extreme environments, like a neutron star, gravity is better understood as a distortion of space-time itself. The mass of the neutron star is so concentrated that it curves the space around it in a measurable and dramatic way. Anything that moves near it must follow that curvature. This includes light. Under normal conditions, light travels in straight lines. It does not bend or slow in ways we can easily notice. But near a neutron star, the curvature of space-time is so strong that light no longer follows straight paths. Instead, it bends around the star, creating effects that would seem impossible in ordinary environments. An observer watching from a distance might see parts of the neutron star that should be hidden behind its horizon. Light emitted from the far side can curve around the star and reach the observer. In this sense, the neutron star reveals more of itself than its geometry should allow. This bending of light is not just a visual effect. It is evidence of how deeply the star alters the structure of space itself. But even more profound is what happens to time. Near a neutron star, time does not pass at the same rate as it does far away. The stronger the gravitational field, the slower time moves relative to an outside observer. This effect, known as gravitational time dilation, becomes significant in such extreme conditions. If you were somehow able to observe a clock on the surface of a neutron star from a safe distance, you would notice that it appears to tick more slowly than your own. Seconds on the surface stretch out when viewed from afar. The difference is not just theoretical. It is measurable and real. From the perspective of someone on the neutron star, however, nothing would seem unusual. Time would feel normal. Processes would occur at their expected pace. It is only when comparing between different gravitational environments that the distortion becomes clear. This creates a strange kind of separation between perspectives. Events that appear slow from one point of view may feel completely ordinary from another. The closer you move to the neutron star, the more pronounced this effect becomes. Time gradually stretches, diverging from the flow experienced elsewhere in the universe. The difference is not infinite, as it would be near a black hole. But it is still significant enough to alter how events unfold. Light is also affected in another way. As it escapes the gravitational pull of the neutron star, it loses energy. This loss does not happen through friction or resistance, but through the influence of gravity itself. The wavelength of the light increases, shifting it toward the red end of the spectrum. This effect is known as gravitational redshift. To an observer far away, light from the neutron star appears slightly altered, its energy reduced as it climbs out of the gravitational well. This shift provides valuable information about the strength of the star's gravity and the nature of its surface. But beyond measurement, it reveals something deeper. Even light, which we often think of as constant and unchanging, is affected by the presence of extreme mass. Nothing escapes influence. Not matter, not energy, not even time. If you were to imagine approaching a neutron star, these effects would become increasingly noticeable. At first, they might seem subtle, barely distinguishable from normal conditions. But as you draw closer, the distortion becomes more pronounced. Distances may appear altered. Light paths curve. The surrounding stars might seem shifted from their expected positions. The universe itself begins to look slightly different, not because it has changed, but because the space through which you observe it has been reshaped. Your own perception of time would remain consistent from your point of view. But to someone watching from far away, your movements would appear slowed. Every action would stretch out, taking longer than expected. Communication between these two perspectives becomes complicated. Signals sent from the neutron star take time to escape, and their frequencies shift as they do. The messages become distorted, stretched, altered by the journey through curved space-time. In this way, the neutron star creates not just a physical boundary, but a kind of temporal boundary as well. A region where time itself is not shared equally. These effects are not unique to neutron stars. They occur wherever gravity is strong enough to significantly curve space-time. But neutron stars represent one of the most accessible environments where these effects can be studied in detail. They are not hidden behind event horizons. They do not prevent observation entirely. Instead, they allow us to see how relativity operates under extreme conditions. Through careful measurement of light, timing of pulsars, and observation of surrounding matter, scientists can test theories of gravity in ways that would not be possible elsewhere. And so far, those theories have held. But they are being pushed. Because the closer we look, the more extreme the conditions become. And the more extreme the conditions, the more likely it is that something unexpected will appear. The distortion of time and space around a neutron star also has implications for what happens inside it. If gravity can alter the flow of time at the surface, what happens deeper within, where density and gravitational intensity increase even further? Does time slow more? Does space curve more dramatically? Or do entirely new effects begin to emerge? These questions are difficult to answer, not because they lack importance, but because they involve conditions that are incredibly difficult to model. The combination of general relativity and quantum mechanics becomes especially complex in such environments. Each theory works well on its own, but together, under these extremes, they begin to challenge one another. This is part of what makes neutron stars so valuable to science. They are places where our understanding is tested. where established theories are applied at their limits, and where the possibility of new physics begins to appear. But while the distortion of time and space shapes the environment around the neutron star, it is only one part of the story. Because there is another force at work here. A force that does not just bend light or slow time, but actively reshapes matter itself. A force that can twist, stretch, and influence particles at the most fundamental level. This force is the magnetic field. And in neutron stars, it reaches strengths that are almost impossible to imagine. After everything we have explored, collapse, explosion, compression, gravity, time, and matter itself, we arrive at a place where the answers begin to fade. A neutron star is not just an object. It is a boundary. It represents the limit of what matter can become without completely disappearing into a black hole. It is the final state where structure still exists, where particles still resist, where the universe holds itself together at the edge of collapse. But beyond this edge, certainty begins to break. Inside a neutron star, we have followed matter as it transforms from atoms into nuclei, from nuclei into neutrons, and possibly from neutrons into something even deeper. Each step takes us further away from the familiar and closer to a reality that is no longer directly observable. We have models. We have equations. We have predictions. But we do not have confirmation. The core of a neutron star remains hidden, not just physically, but conceptually. It exists under conditions where our current understanding of physics begins to stretch. The forces involved, gravity, quantum mechanics, nuclear interactions, are all operating at their extremes, and their combined behavior is not fully understood. This is where neutron stars become more than scientific objects. They become questions the universe is asking. Is there a limit to how dense matter can become? Do neutrons remain stable under all conditions? Or do they break apart into their constituent quarks? Could entirely new forms of matter exist, stable only under these extreme pressures? Or is the neutron star itself only a temporary state, destined to collapse further given enough time or additional mass? These are not abstract ideas. They are active areas of research, explored through observation, simulation, and theory. Every new measurement of a neutron star's mass, radius, or behavior adds another piece to the puzzle. Every pulsar signal, every gravitational wave detection, every subtle shift in radiation brings us slightly closer to understanding. But the closer we get, the more complex the picture becomes. Instead of clear answers, we find deeper layers of uncertainty. There is also something else that neutron stars reveal, something less technical, but equally profound. They show us that the universe is not limited by our intuition. The way matter behaves on Earth, the way time feels, the way forces interact. These are not universal experiences. They are local conditions. Under different circumstances, reality itself can take on forms that seem almost impossible. A neutron star is a reminder of that. It shows us that the familiar structure of atoms is not permanent, that space and time are not fixed, that the laws of physics, while consistent, can produce outcomes far beyond what we naturally expect. And yet, despite their extremity, neutron stars are not isolated curiosities. They are part of a larger story. The material ejected during their formation becomes part of the cosmos. The elements created in their explosive births spread across space, eventually forming new stars, planets, and perhaps even life. The processes that occur inside them influence the evolution of galaxies and the distribution of matter throughout the universe. In this way, Neutron stars are both endings and beginnings. They mark the death of massive stars, but also contribute to the creation of everything that follows. There is a final perspective worth considering. If you could somehow observe a neutron star from a safe distance, watching its steady pulses, measuring its radiation, tracking its motion, it might seem predictable. A stable object, governed by known laws, behaving in measurable ways. But that perspective is incomplete. Because beneath that calm exterior lies a reality we cannot directly access. A reality where matter is compressed beyond recognition, where forces interact in ways we are still trying to understand, and where the boundary between known physics and unknown possibility remains unclear. That hidden interior is what makes neutron stars truly remarkable. Not just what they are, but what they might be. In the end, the question we began with, what happens inside a neutron star, does not have a single, final answer. Instead, it leads us through layers of understanding, each one revealing something new, each one raising further questions. We can describe the surface, we can model the crust, we can theorize about the core, but the complete picture remains just out of reach. And perhaps that is what makes it so compelling, because it reminds us that even in a universe we have studied for centuries, there are still places where knowledge fades into mystery, where understanding gives way to exploration, and where the most extreme objects are not just answers, but invitations to keep searching. As we look out into the universe, these distant, dense stars continue to exist quietly, spinning, emitting signals, holding within them secrets that have yet to be uncovered. They do not announce their mysteries. They simply wait. And slowly, through observation and discovery, we move closer. Not to a final answer, but to a deeper question. And perhaps that is the true significance of a neutron star. Not just what happens inside it, but what it reveals about the limits of our understanding.